Welcome, welcome, deeply curious minds. And wow, can you believe it? This is our 100th deep dive together.
100. It's quite a milestone.
It really is. 100 journeys into the heart of some fascinating subjects, pulling out those key insights. Today, though, we're doing something special. We're not just diving deep. We're taking this monumental leap across centuries of human ingenuity.
From ancient wonders to modern marvels.
Exactly. From the sheer, raw power it took to build something like a Roman vault, maybe using just basic windlasses, compared to a modern engineer designing a skyscraper in this incredibly detailed virtual world. A world that can predict every stress point before a single beam is even ordered.
It's a breathtaking arc, really. Shows that enduring human spirit of creation.
It does. And marking our 100th dive with this topic feels right, doesn't it? Because to really grasp where we're going in the built world, well, you've got to appreciate where we've come from.
Absolutely. This deep dive, it's all about tracing that powerful, continuous line, the through line, if you will, that connects the foundational wisdom of someone like, say, Vitruvius.
Right, the Roman architect.
All the way to the cutting-edge data you get from a modern digital twin. So we've invited you, our listener, to join us in what we're kind of calling a capstone conversation.
Hey, capstone. I like that.
Yeah, it's not just looking at another set of sources. We're aiming for a unique roundtable feel, synthesizing insights from experts across our previous dives to really reflect on the history and, crucially, anticipate the future of how we build.
That emphasis on understanding the past feels so important, especially now with technology moving so fast. Our mission today, really, is to understand this whole evolution. Which core ideas have stuck around? Which ones have actively shaped our progress, even as, the tools have changed beyond recognition?
Precisely. Think of this dive as a celebration of the people, the big ideas, the innovations that have shaped our built world for thousands of years.
And looking ahead, too.
And definitely looking ahead. It's an inspiring look at the best practices that are going to define the next century. Our core philosophy for the show holds true. To build a better future, you first have to understand the foundations of the past. We'll see how ancient principles still echo even in the most advanced digital stuff today.
Okay, let's dive into those foundations. The enduring wisdom that's guided builders forever. When you talk ancient principles, there's one name that just stands out, right? Vitruvius. His ideas are still debated, still taught. His influence is, well, it's timeless.
Oh, without a doubt. If you want a touchstone for architectural principles that last, Vitruvius and his work De Architectura, that's your source. His famous triad, firmness, utilitas, and venustas.
Which translate to
durability or strength, firmness, utility or commodity, utilitas, and beauty or delight, venustas. And the crucial thing is these aren't just like abstract aesthetic guidelines. They're fundamental practical necessities for any successful building, no matter the era.
So break those down a bit. Firmness.
Right, firmness is about the physical stuff. Strength, stability, integrity. Can the building stand up to time, to the weather, to, whatever forces act on it? Will it last?
Makes sense. Utilitas.
That's about function. Does it work? Does it serve the purpose it was designed for? Shelter, business, worship, whatever. How well does it meet those needs?
Got it. And venustas.
That's the beauty, the aesthetic appeal. Does it delight the eye? Does it lift the spirit? Does it fit well in its surroundings? But here's the key. They're not separate things you check off a list.
They're integrated.
Exactly. Deeply integrated qualities. You need all three for a truly successful, enduring building.
It's striking how complete that is. But Vitruvius wasn't just being philosophical, was he? I mean, his writings get incredibly specific. It sounds less like theory and more like a builder's handbook.
Oh, absolutely, not just philosophy. And that's a huge part of why his work endured. It's packed with practical, detailed advice. It clearly comes from, tons of experience and deep knowledge of Roman construction.
Like what kind of details?
Well, for instance, he talks about the exact proportions for an atrium specifying dimensions, like 170 feet for certain types, or he gives really careful guidance on where you should site a temple, say for a temple of Bacchus, the god of wine and revelry. He might suggest a spot that's naturally shaded, maybe near running water, connecting it to Bacchus's ties to nature. This level of detail shows that ancient architectural guidance was rooted in both sophisticated structural understanding and a deep feel for the human experience within the space.
It's holistic.
It really is. It weaves together these grand ideals with very practical, buildable instructions, making sure the thing not only stood up, but also worked well and looked good doing it.
Okay, so those are the big Vitruvian virtues.
Yeah.
How did we see those play out in actual structures over time? How did form and function evolve from, say, those massive Roman vaults to the incredible medieval cathedrals?
That's a great question because you can absolutely trace a clear thread of evolution. Let's start with the Romans and their vaulted long halls. Think about the Alla Triana in Trajan's markets. Then maybe the Frigidarium, the cold room and the baths of Caracalla, huge structure, and then culminate with the Basilica of Maxentius and Constantine, just massive.
Right.
Looking at that sequence, you see this continuous push towards greater height, towards getting more window space, making these big, light-filled interiors. The Romans were constantly pushing the limits of concrete and vaulting tech to create grander, more functional public spaces.
And it wasn't only long halls, was it? They were masters of domes, too, centrally planned buildings.
Precisely. There's a parallel evolution there. It starts maybe with that bold octagonal room in Nero's Golden House and leads right up to the Pantheon. An icon, still standing, that amazing unreinforced concrete dome. And from there, the form spreads. You see it in Hadrian's Villa, the Caldarium, the Hot Room, at Caracalla, influencing later mausoleums too.
And the trend there was similar, height and light.
Yes, again, this increasing desire for monumental height, more windows for light, but also, critically, Kostov points this out, the opening out of the domed core into semi-independent border spaces.
What does that mean exactly?
It means creating more complex, sort of flowing interiors. The central dome wasn't just a closed-off space. It connected to surrounding niches or rooms, making the whole experience more intricate, giving you both grandeur and spatial complexity.
Incredible scale and ambition. But then, fast forward a few centuries, and you get medieval builders, especially in the Gothic period, doing something radically different with vaults to get those soaring cathedrals.
Yes, the big leap there was the pointed arch. Spiro Kostov lays this out beautifully. Pointed arches have significant structural advantages over the semicircular, round-headed arches the Romans often used.
How so?
Well, a round arch, if you try to stretch it to cover a wide space, tends to flatten out at the top, wants to push outwards really strongly, so you need massive, thick walls to hold it in.
Right, I can picture that.
But a pointed arch, because it's struck from two centers, it maintains a steeper curve. It channels the weight, the thrust, much more downwards.
Oh.
This means you can span wider areas and go much higher, all with less outward push. That's what allowed for those signature Gothic features. The incredible height, the thinner walls, and those huge expanses of stained glass. It unlocked a whole new dimension of building.
That's a fantastic structural insight. And it reminds me of Viollet-le-Duc's take on the difference between Roman and Greek approaches. He saw the Romans more as pragmatic constructors.
Exactly. Viollet-le-Duc, the great French architect and theorist, he argued the Romans were mainly focused on the practical side, on efficiency for building on a massive scale. Once they found a method that worked reliably, they'd just keep repeating it, sometimes for centuries, even if it wasn't maybe the most structurally elegant or purely rational approach.
Compared to the Greeks.
Compared to the Greeks, yeah, whose approach he saw as more instinctual and rational. Rooted in artistic principles, in a constant logical refinement of form based on a deep grasp of materials and how structures actually work. For Viollet-le-Duc, the Romans focused on the how to build big efficiently. The Greeks focused more on the what and why, the art, and the structural logic.
And he wasn't afraid to critique Roman engineering, even on something as monumental as the Basilica of Constantine.
Not at all. He had an incredibly sharp eye for structural integrity. While acknowledging Roman skill, he pointed out what he saw as a flaw in the Basilica of Constantine. He questioned putting rigid supports, these huge monolithic columns of granite or marble, right under the point where the massive vault starts to spring upwards.
Why was that bad?
He argued, and remember, he's looking back with centuries of structural understanding, that those rigid columns would have been much better placed outside against the buttresses. His reasoning was clever. If that enormous concrete structure settled even a tiny bit, those inflexible columns couldn't give or compress. They'd basically force the whole vault structure to push outwards and fail, especially with the enormous concrete homogeneous mass the Romans were using. It shows his deep understanding of how different parts of a structure interact under load. Strength isn't everything. How you assemble it is critical.
So if the Romans were these super practical builders, maybe making compromises Viollet-le-Duc didn't love, how did a masterpiece like Notre Dame de Paris come together? He described it as built with knowledge, taste, study, care, resolution, and experience, and relatively quickly for its time.
For Viollet-le-Duc, Notre Dame was the absolute pinnacle of French art and engineering. It wasn't just a big building, it was a colossal structure designed and built with profound architectural integrity, aesthetic genius, and this amazing depth of understanding about craft, materials, purpose, everything.
A complete harmony.
Yes, a complete art, totally in harmony with the needs of its society. He saw it embodying this noble order where every single detail, from the structure, those innovative flying buttresses to the sculpture, all worked together cohesively. It was a project where advanced engineering and profound art weren't just mixed, they were symbiotic.
Mhm.
That ability to combine the grand vision with sound construction and masterful execution and do it relatively fast, that's what made Notre Dame an exemplar for him.
That synergy between the material and the intellectual, that's powerful. Okay, let's zoom in from the scale of cathedrals to the actual materials. The raw stuff and the intimate knowledge the artisans had. This is where you see that deep traditional understanding.
Oh, absolutely fundamental. This deep, almost intuitive grasp of materials is key, and it's a lesson that spans all of history. Think about basic traditional construction elements, the kind Francis D.K. Ching details so well. Foundation walls, for example. Cast-in-place concrete. It's not just pouring goo into a hole. You need precisely built formwork, the molds, to shape it. And you need anchor bolts embedded perfectly to attach the sill plates later for the frame. Precision is everything.
Or wood joists for floors.
Exactly. Wood joists the beams holding up floors and ceilings. Their spans, like knowing a 2x6 can go about 10 feet, or a 2x12 maybe 18 feet, those weren't random. Builders developed these rules of thumb, like estimating joist depth as, say, span divided by 16. Quick, practical.
But it wasn't just about whether it would break, right?
No, that's crucial. It wasn't just about strength. Deflection, how much the joist bends under load, was huge. The rule was often deflection shouldn't exceed 13/60th of the span. Why? Because a flow that bounces or sags feels awful, and it can crack plaster or pop tiles, even if it's technically strong enough.
So stiffness was often more important than pure strength.
Often, yes, which led to using deeper joists, maybe spaced further apart. It's about the whole system feeling solid and comfortable. Even the concrete formwork, sometimes custom-built, but often prefabricated panels for efficiency, needed robust bracing to hold its shape until the concrete cured. Details matter.
That level of detail for something like a joist is kind of mind-blowing. And it's not just the dimensions, it's the wood itself, right? The grain, the knots. Craftsmen had to read.
They're remnants of branches, and yeah, they have a huge impact. They're classified based on how they look. Spike knots if they run along the board, round knots if they're circular, pin knots if they're tiny. A good craftsman understands these, knows how they affect strength, stability, workability. You learn to avoid flaws that could ruin a piece of furniture or even a structural beam.
It sounds like reading a language.
It really is. A skilled woodworker, maybe after years, can look at the bark, the growth rings near the center, and pretty much predict internal flaws. It's an almost intuitive understanding.
And this deep knowledge wasn't just about common woods like oak or pine, right? It was incredibly regional, tied to whatever materials were available locally.
That's a critical point. Alec Clifton Taylor's work, The Pattern of English Building, shows this beautifully. Building practices were intimately tied to local geology. It wasn't just convenient, it shaped entire architectural styles.
Like how?
Well, take Oxford. It's famous for that warm, honey-colored stone, right? That's mostly local Corellian oolite, a type of limestone. Easy to work, gives the city its look. Or go to Dorset, you find Marnhull and Todbur freestone used everywhere in old churches again. Local stones known for being good to carve and lasting well.
And roofing.
Up in Derbyshire, especially from Carboniferous rocks, they used sandstone slates, thackstones, for roofing for centuries. That's just what the local geology provided. Even brick making was often hyper-local. At Kirby Muxloe Castle, they literally made the bricks on site from local clay.
Wow.
It shows incredible ingenuity in using what's around, but also the development of really specialized skills tied to those specific local materials. Geology-shaped craftsmanship.
Okay, so we have the materials, the craft. But how did they manage the whole process? Organizing these huge, complex projects before computers, before modern project management tools. Let's talk about early project management.
Well, the core role of construction management, even as described in modern sources like the Construction Management Jumpstart, is fundamentally timeless. Even way back, someone, the master builder, an overseer, had to interpret the plans, even if they were simple drawings or just verbal instructions.
Right.
They had to estimate costs, probably based on experience, figure out rough timelines, decide the best way to get things done considering time, cost, quality. And crucially, oversee everything, coordinate all the different trades, keep it safe. Those core functions, planning, estimating, scheduling, coordinating, quality control, they haven't really changed, even if our tools are way more sophisticated now.
So who were the key players coordinating all this? Was there someone like a general contractor back then?
The role of the general contractor or prime contractor definitely has historical roots. This was the person or group who contracted with the owner to deliver the project based on the plans. Historically, the master builder often played this role, responsible for the big picture and execution.
Did they do all the work themselves?
Sometimes they do some of it, what we call self-performed work, maybe leading the masons or carpenters directly, but it was also common, even in ancient times, to bring in specialists. Think about stone carvers, mosaic artists, fresco painters for highly skilled tasks.
Subcontractors, essentially.
Exactly. Today, a GC might mostly manage things with their own field staff, and subcontractors do most of the actual trade work. But that basic idea of dividing labor based on specialized skills goes way back.
And scheduling. Even rudimentary scheduling might have existed. We think of things like the critical path as modern, but the basic ideas had to be there, right?
They absolutely had to be, even if they didn't use our terms. Concepts similar to modern scheduling were definitely used implicitly to manage projects like Roman aqueducts or Gothic cathedrals. Take float, the wiggle room an activity has before it delays the whole project. Modern PM talks about interfering float versus independent float, depending on how a delay affects other tasks. And the critical path itself, the sequence of tasks where any delay pushes back the whole project finish date. Even without software, experienced builders knew some things just had to happen before others.
Like the foundation before the walls.
Exactly. Foundation first, then walls, then roof. That basic dependency logic was understood. They knew which tasks were critical to keeping the whole thing moving forward and where they had a bit more flexibility. It was essential for managing timelines and resources, even if it was tracked in someone's head or on rough tallies.
That makes sense. And wasn't there an early method that kind of anticipated modern lean thinking, focusing on the output rate?
Yes. The line of balance method.
Yeah.
A fascinating example of early efficiency thinking. It actually came from manufacturing in the 1940s, got picked up by the U.S. Navy for shipbuilding, a massive coordination effort, and then introduced to construction, first in the UK, around the late 60s. Because it came from manufacturing, it had a different perspective. It started with the end product in mind.
How did that work?
The first step was creating an objective chart. This was basically a plan showing how much finished work, say how many completed housing units or floors of a building should be delivered over time. It used visual charts to track the rate of production across repetitive units rather than just focusing on the duration of individual tasks.
So focusing on flow.
Exactly. Focusing on the flow of value, maintaining a steady production rhythm, identifying bottlenecks. It's a clear forerunner to modern lean construction principles, which are all about value flow, eliminating waste, and continuous improvement.
Okay, so we've journeyed through millennia, Vitruvian principles, Roman vaults, medieval craft, early management. It's such a rich history. But now, what does it all mean for today? And maybe more importantly for tomorrow? Because the tech acceleration we're seeing now, I mean, it would just blow those ancient builders' minds, wouldn't it?
Oh, completely. We've gone from parchment blueprints to these interactive, predictive digital environments. It's a different world.
The pace of change is just exponential, and it's reshaping everything.
It really is. And one of the absolute biggest game changers highlighted in the BIM handbook is building information modeling, or BIM.
Right, BIM.
And it's so important to get this. BIM is way, way more than just fancy CAD, computer-aided design. Traditional CAD systems let you draw 3D objects, sure. But BIM embeds intelligence into those objects.
Intelligence, how so?
It means a wall in a BIM model isn't just lines. It's an object that knows things. It knows its material, its thermal properties, maybe its cost, how it connects to the structural system, the plumbing system.
Ah, okay. It connects different disciplines.
Exactly. It moves beyond single discipline design. Tools like Revit, Bentley, Vectorworks have matured now to integrate architecture, structure, MEP, that's mechanical, electrical, plumbing, all at an object level. It's about the information behind the geometry.
So it's less about drawing lines and more about creating this, like, intelligent digital database for the building.
You've got it. A BIM environment is really about managing data comprehensively. It's an integrated information pipeline connecting different software, different teams, supporting policies for how information flows through the whole project lifecycle.
And it's not just model data.
No, not at all. It can carry all sorts of project information, video walkthroughs, photos, audio recordings of meetings, key emails, not just geometry and materials. Plus, it includes libraries of standard objects and assemblies you can reuse, and critically, it often links directly to the company's management and accounting systems. It's a whole data ecosystem.
Okay, this is where my mind starts to bend a bit. We hear about digital twins. Is BIM basically the foundation for creating a living, breathing digital replica of a building?
That's exactly where it's heading, and BIM is the essential enabler, a digital twin.
Yeah, imagine a virtual replica that's dynamically linked to its physical counterpart.
How does BIM make that possible? Well, think about large teams working together on one shared master model. BIM enables this through things like concurrent versioning systems or CVS smart ways to manage file changes, so multiple people can work at once without messing each other up. And you can load different parts of the model, maybe look at it floor by floor, or just see the HVAC system, or just the electrical.
So you build this super detailed virtual model.
Right. And then the twin part comes in when you connect it to the real building, often through sensors. So the digital model gets real-time data from the physical building temperature, energy use, occupancy, structural stress.
Wow.
It becomes a living model that mirrors the real thing throughout its entire life: design, construction, operation, even eventual demolition. You can use it for predictive maintenance, optimizing performance, running what-if scenarios. It's incredibly powerful.
And even before you get to that full twin stage, BIM offers huge practical benefits right now, doesn't it? Especially for coordination, which is always a headache in construction.
Oh, massive benefits. The CMAA standards point this out clearly. First, clash detection. BIM systems can automatically find conflicts between different designs.
Like a pipe hitting a beam.
Exactly, like a structural beam scheduled to go right where a major duct needs to run. BIM finds that clash in the virtual model before it becomes a huge, expensive problem on site. That saves enormous amounts of time and rework.
That alone sounds worth it.
It often is. And second, it supports virtual hard-at reviews. Basically, you can do these immersive walkthroughs of the digital model. Owners, future occupants, facility managers, they can all walk through the building long before it exists physically.
So they can spot issues early.
Precisely. They can check layouts, see if equipment access is okay, understand the space. It helps everyone visualize the project, make better decisions, and minimize those costly changes that always seem to pop up after construction starts. It makes the whole design review process way more effective.
Incredible. So if BIM and digital twins are where we are now, what's next? You mentioned something called declarative design. That sounds like a really fundamental shift.
It is. Declarative design, or sometimes called generative design, is a really different way of thinking about creation. Neil Gershenfeld at MIT talks about this a lot. Instead of drawing how something should look or be made, you specify what you want it to do. It's performance criteria.
Give me an example.
Okay, think about designing an airplane. Instead of drawing the wings and fuselage, you'd tell the system, I need it to fly at this speed, carry this much load, have this range. Then the system, using complex algorithms, explores maybe millions of possible shapes and structures that meet those performance goals, often coming up with designs a human might never have conceived.
So the computer generates the form based on the function.
Essentially, yes. We're getting better at handling the curse of dimensionality, managing tons of variables. The vision is for computation and fabrication to merge, allowing this kind of continuous online design and evolution. The design isn't fixed. It can adapt and improve based on new data or constraints.
And this connects to ideas about future fabrication too, right? Not just better 3D printers.
Exactly. It's much deeper than just additive manufacturing. Gershenfeld talks about a future personal fabricator, not as just a machine that lays down plastic, but as a system that could potentially code the construction of materials itself.
Code materials, what does that mean? Like programming atoms?
It sounds like science fiction, but that's the direction. Imagine being able to program the properties of a material on demand, assembling it from more fundamental components. This would radically change everything: less reliance on huge inventories of raw materials, drastically less waste, because you create exactly what you need with the properties you need.
Wow.
It taps into John von Neumann's ideas about self-replicating machines, what Gershenfeld calls evolving bits arranging atoms. The digital world directly manipulating the physical world at a fundamental level. It could transform supply chains, manufacturing, sustainability, everything.
Fascinating. if a bit mind-bending. Okay, from programming atoms, let's shift to a different kind of programming. Building for the long haul for future generations. Sustainability. This feels absolutely critical.
It is critical. And sustainable construction really stems from that core idea of sustainable development, famously defined in the UN's Our Common Future report back in the 80s.
Which is?
Meeting the needs of the present without compromising the ability of future generations to meet their own needs. It forces us to think about intergenerational justice. How far ahead should we be considering the impact of what we build today?
There's that Native American concept, right? Thinking 7 generations ahead.
Exactly. That philosophy, thinking about 200 years into the future, really puts it in perspective. It makes you ask, are the materials we're using today going to be valuable resources for our great-great-grandchildren, things they can recycle or reuse? Or are we just creating massive waste disposal problems for them? That choice between short-term convenience and long-term stewardship is really the heart of the green building movement.
So how do we actually measure that? How do we encourage sustainable practices beyond just good intentions?
That's where green building rating systems have played a huge role. You've probably heard of some HULID in North America, BREEAM in the UK, Green Globes, the Living Building Challenge.
Right, the checklists.
Yeah, they often work as detailed checklists of measures, energy efficiency, water use, materials, site impact that a project team can follow to get certified as green. And they've been incredibly successful in pushing green building into the mainstream market by providing clear criteria and a recognized standard.
But are there downsides to the checklist approach?
There can be. Charles Keibert, who's a leader in this field, points out that just following a checklist without a deeper understanding of ecological design principles can sometimes lead to building stereotypes. Kind of cookie-cutter green buildings that meet the letter but maybe not the spirit and don't push innovation. He really advocates for design rooted in understanding natural systems, which he argues leads to better buildings both economically and aesthetically. Go beyond compliance to true performance.
So beyond ticking boxes, what are some practical examples of sustainable building practices on the ground or in the building science?
Well, on-site, it means things like rigorous site protection plans, controlling erosion, managing sediment runoff during construction. It means detailed health and safety plans for workers. And crucially, construction and demolition waste management plans, aiming to divert huge amounts of waste away from landfills through reuse and recycling. That's about minimizing impact during the build.
In the building itself, energy efficiency.
That's where building science comes in, as detailed by experts like Joseph Ostibrick. It's about the building envelope working as a system. You need effective thermal barriers to slow heat flow. You need robust pressure boundaries or air barriers to stop uncontrolled air leaks, which waste huge amounts of energy. It's about placing ductwork inside the conditioned space, not in hot attics or cold crawl spaces where energy just bleeds away. And understanding vapor retarders where to put them depends crucially on your climate. Cold climates need them on the inside to stop moisture getting into the wall. Hot, humid climates might need them on the outside. Get it wrong, and you trap moisture, leading to mold and rot.
And ventilation.
Critical for healthy indoor air, but it needs to be done efficiently, often with heat recovery ventilators, so you're not just pumping conditioned air outside. All these layers, insulation, air sealing, vapor control, ventilation, have to work together.
And this isn't just about being green, right? There are real economic benefits to building this way.
Absolutely. That's a key driver. Keibert demolishes the myth that green building is always way more expensive with no return. He cites examples where the annual energy savings in a high-performance green building actually equaled the extra construction cost.
So a payback period of just over a year.
Exactly, which is incredible. It shows that investing in good design, efficient systems, proper commissioning to make sure everything works as intended, managing waste well, it's not just environmentally sound, it's economically smart. It offers rapid financial returns.
And materials.
Materials matter too. Things like laminated wood are often highlighted strong, durable, cost-effective, uses wood efficiently, and it's potentially recyclable or reusable down the line. Smart, sustainable choices often make good long-term economic sense.
Okay, so we have smart tech, sustainable materials and methods. But none of this happens without people working together. Let's talk about the workforce and this shift toward a more collaborative culture. This sounds like it's really changing how projects get delivered.
The human side, the culture, it's absolutely central. We're seeing a big move towards what are called alternative project delivery methods, things like at-risk CM, construction management, or design build.
How are they different?
The key difference is they intentionally overlap the design and construction phases, rather than keeping them totally separate like in traditional design bid build. The whole point is to manage risks better, find efficiencies, generate more value, and cut waste.
How does overlapping help?
Because it forces collaboration early on. These methods emphasize pre-construction activities. That means the contractor, key trade partners, maybe major suppliers, they get involved during the design process. They bring their practical knowledge to the table.
So the builders are advising the designers.
Yes, they can offer input on constructability. Is this design actually easy and efficient to build? On material choices, on system options, considering not just the upfront costs, but the whole life cycle performance and maintenance. This avoids designing something that looks great on paper, but is a nightmare to build or operate.
That sounds like it demands much more communication and coordination, maybe stronger leadership than the old way where everyone stayed in their silos.
It absolutely requires it. The CMAA standards really stress the construction manager's role in providing that coordination and leadership. Establishing crystal clear lines of communication is job one. Making sure information flows properly, preventing people from going around the process, which just leads to confusion and mistakes.
And meetings. Lots of meetings.
Structured meetings are key. Not just endless meetings, but purposeful ones. Pre-construction meetings to get everyone on the same page about procedures. Regular progress meetings to track the schedule, coordinate upcoming work, tackle problems proactively, special meetings for urgent issues. It's all about fostering an environment where information flows and decisions get made effectively.
And bringing in those specialty contractors early, that really leverages their expertise, doesn't it? Gets their real-world smarts into the design.
A huge difference.
Yeah.
Lean construction research really backs this up. When you involve specialty trades early, they bring insights into process efficiencies or quality improvements that the architect or GC might never think of.
Like what?
Maybe the HVAC contractor sees a way to route ductwork during design that saves tons of installation time later. Or the curtain wall supplier suggests a slight design tweak that improves weatherproofing and simplifies installation. It counters that old piecemeal contracting mentality where you just get bids for separate parts.
Right.
Instead, you design the whole project as an integrated system, optimizing how all the pieces work together, not just optimizing each piece in isolation. That leads to much better outcomes overall.
So what does this shift mean for the folks actually doing the work? And how do you manage risk in these more complex, collaborative setups?
Construction is inherently risky. For the workforce, it means fostering a culture that's proactive about risk and encourages learning. Risk management isn't something you do once. The CMAA emphasizes it's a continuous, structured process built into project management right from the start. You systematically identify potential problems, schedule, budget, materials, site conditions, whatever, and you figure out timely, cost-effective ways to deal with them before they blow up. It needs the same level of attention as budgeting and scheduling. Be proactive, not just reactive.
And safety, of course, remains paramount.
Absolutely non-negotiable. A robust written safety program with proper training for the specific hazards on that project is essential. On big projects, you might see owner-controlled insurance programs, OCIPs, which often bring a more unified, stringent approach to safety across all contractors.
Beyond the formal programs, there's also this interesting tension, maybe, between relying on data and algorithms versus trusting hands-on experience.
That's a really fascinating point, and Matthew Crawford writes beautifully about this in Shop Class as Soulcraft. We're constantly balancing intuitive judgments, that gut feeling, the wisdom born from years of working with materials against algorithms and data analysis. Algorithms are powerful for complex systems with tons of variables, but Crawford cautions against relying only on them.
Why?
Because that hands-on wisdom, that immediate understanding of cause and effect you get from physical work is invaluable, especially when dealing with unexpected site conditions or tricky materials. The real challenge for the future is integrating both leveraging data and respecting and incorporating that deep, tacit knowledge of experienced craftspeople. Don't lose the human touch, the craft intelligence.
Okay, let's zoom out again. We've talked buildings, teams, materials, tech. What about the whole city? How are these smart concepts, this data revolution, shaping the entire urban landscape?
This is where we get into the smart city idea, which Carlo Ratti and Matthew Claudel explore so compellingly in The City of Tomorrow. We're generating unbelievable amounts of urban big data now from almost everything. Traffic sensors, transit card swipes, energy meters, environmental monitors, even social media check-ins. fueled by fiber optics, wireless networks, open databases. This data allows us to sense urban life in real time on a massive scale, far beyond old-school surveys. And importantly, it can empower citizens to understand and shape their own environments, fostering bottom-up innovation.
So a smart city isn't just about tech gadgets. It's about this flow of information, making the city somehow alive and responsive.
That's the core idea. A truly smart city has this constant real-time information flow. It uses data to predict future scenarios like traffic jams or energy demand, and it has actuators, digitally controlled things that can physically respond to the data, like adaptive traffic lights or smart street lighting.
And the goal?
The ultimate goal, as Ratty and Claudel put it, is to radically integrate digital systems into architecture, but crucially, to refocus technology on humans, making architecture feel like an extension of the body, using cyborg tools, creating active buildings that act as life support systems, managing energy and air quality, but also as social catalysts, facilitating connections. The built environment becomes dynamic, interactive, constantly adapting to human needs.
That sounds incredibly futuristic, but very human-centric.
Yeah.
How does that vision connect with, say, the ideas of Jane Jacobs? She championed the messy, organic, complex life of cities decades ago. Is this contradicting her?
That's a great question, and it's vital they don't contradict. Ideally, this tech-enabled city enhances rather than replaces Jacobs' vision. Remember, Jacobs celebrated neighborhoods as living organisms full of intricate connections, diverse uses, spontaneous interactions. She hated sterile, top-down planning. A smart city, if done right, uses technology to understand and support that very complexity. It can help facilitate those chance encounters, make public spaces more adaptable, give citizens the data to advocate for their neighborhoods. The tech should serve the human-scaled, vibrant, diverse, urban life Jacobs valued, helping us understand the city's pulse in ways she could only imagine to foster, not fight, that organic complexity.
Okay, so how can these smart city concepts tackle really concrete challenges like managing energy use across a whole city? That's a huge issue.
Energy is a perfect example. The vision is for a truly functional smart grid, not just delivering power one way, but a hybrid system. Buildings might have integrated batteries. Even electric cars, when parked, could act as temporary storage, feeding power back to the grid when needed.
A two-way street.
Exactly. And dynamic energy management. Imagine every kilowatt hour having a variable price based on real-time supplies, the sun shining, wind blowing, and demand. Your smart appliances, your car charger, the building's HVAC system, they'd all communicate with the grid, automatically adjusting consumption slightly to help balance the system, avoid peaks, use power when it's cheapest and greenest. It's about optimizing the whole system, making every part an active, intelligent participant.
This kind of dynamic optimization requires really understanding systems, doesn't it? Feedback loops, unintended consequences.
It absolutely does, and that's where Donella Meadows' work, Thinking in Systems, is so fundamental. She explains concepts like exponential growth, how things can escalate incredibly quickly. And balancing loops, the self-correcting mechanisms that create stability, like a thermostat, understanding how these different loops interact in a complex system like a city is crucial.
And she warns about things not always working as expected.
Yes, counterintuitive behavior. You push on a system here, intending to fix something, and it causes an unexpected problem over there, maybe even making the original problem worse. High leverage, wrong direction, she called it. You need that systemic view to anticipate those ripples before you intervene in complex urban systems like energy, traffic, or housing.
And she talks about the tragedy of the commons, which feels very relevant to construction and urban resources.
Extremely relevant. The tragedy of the commons describes situations where individuals, acting rationally in their own short-term interest, end up depleting a shared resource, harming everyone in the long run.
Like overfishing.
Classic example. Or polluting a shared river or the atmosphere. In construction, Meadows would argue it could be things like choosing the cheapest, most environmentally damaging materials because the environmental cost is externalized, someone else, or future generations pays the price. Or cutting corners on waste management, dumping waste in public landfills instead of investing in recycling. The individual gains by saving money, but the collective resource, clean air, land, future materials suffers, especially when the negative feedback loop is weak or delayed. Understanding this dynamic is key to building truly sustainable cities that encourage stewardship over short-term exploitation.
Wow. Okay, so we've traced this incredible arc. From Vitruvius' timeless principles, Roman engineering feats, medieval craftsmanship, early management efforts, all the way to BIM, Digital twins, generative design, smart, sustainable cities fueled by data and systems thinking. It's been quite the journey across centuries. How do we bring it all together? How do we synthesize this past and this future to actually build better?
That dialogue between history and innovation, that's really the sweet spot. Take Vitruvius again. Firmitas, utilitas, venustas, strength, utility, beauty. Those ancient principles, they're still completely relevant when we talk about a digital twin.
How so?
Well, what is a digital twin, really? It's an incredibly sophisticated tool to help us optimize for exactly those things across a building's entire life. It helps ensure Firmitas through predictive structural analysis. It optimizes utilitas by letting us simulate how the space will actually be used. It can even help assess venustas, maybe through virtual reality walkthroughs, evaluating the aesthetics and user experience. The tools are new, but they're serving those same ancient, fundamental human needs for our buildings.
And that deep knowledge of materials, the craft wisdom honed over centuries, that's not obsolete either.
Not at all. That historical understanding, documented by people like Ching or Hoadley, that deep material intelligence provides an invaluable foundation for today's advanced material science and sustainable design. Understanding how wood behaves naturally, or the properties of different stone, or the chemistry of concrete, that knowledge helps ensure that new materials, maybe developed using AI or advanced computation, still respect fundamental physical realities. It prevents us from making old mistakes in new ways and allows us to innovate from a place of grounded understanding. We're building on that wisdom, not replacing it.
And project management, too. Even the early attempts connect to modern methods.
Definitely. Those early efforts understanding critical dependencies, the line of balance focusing on production flow, they directly anticipate modern integrated project delivery, IPD, and lean construction. We have much more powerful tools now, BIM integrated scheduling, sophisticated risk analysis software, but the fundamental goal is the same. Optimize efficiency, manage cost and risk, ensure quality, deliver projects smoothly. It's a continuous journey of refinement, applying better tools to those enduring challenges.
Okay, so the connections are there. But merging this ancient wisdom with hyperspeed technology can't be seamless. What are the biggest hurdles? Where's the friction in uniting past and future?
A huge one, as Neil Gershenfeld points out, is simply that institutions have been slow to change. Our laws, economic models, regulations, even cultural habits, they often lag way behind what technology makes possible. This inertia can block innovation. Overcoming it isn't just about having brilliant engineers. It's about, as he says, galvanizing a generation, getting people engaged with science and tech, not just as consumers, but as active shapers of the future. It's a societal challenge.
And there's maybe a risk of focusing too much on the tech itself, losing sight of the bigger architectural or urban picture, the why behind it all.
That's a critical danger. It reminds me of Viollet-le-Duc warning against getting lost in the trivial details of archaeology. It was this metope, blue or red. Instead of understanding the principles behind the style, the civilization it came from, future construction needs both. The deep, hands-on material understanding of the past and the analytical, intellectual power of new tech. We need to make sure technology serves genuinely human and architectural goals, beauty, function, community, sustainability, not just novelty for its own sake.
But if we can navigate those challenges, the opportunities must be immense. If we successfully weave together this wisdom and tech,
The opportunities are transformative. We could be looking at what some call collaborative futurecraft, using these digital tools not just top-down, but to empower bottom-up actions, enabling smart citizens, as Ratty and Claudel envision. It's about designing with people at the center, using tech to create environments that are more responsive, equitable, adaptable, and genuinely sustainable for everyone, harnessing collective intelligence in new ways.
and could also shift how we think about the economics of building towards longer-term value.
Hopefully, yes. Stuart Brand's idea of gradual money versus cataclysmic money feels relevant. We need building economics that values long-term stewardship, steady investment in maintenance, adaptation, resilience, over just maximizing profit at the moment of sale. Thinking about the building's life, not just the deal. Ultimately, it loops back to what people like Le Corbusier called for, addressing the fundamental need for shelter, comfort, and well-designed environments for everyone to maintain the balance of society. Integrating past wisdom with future tech gives us an unprecedented chance to achieve those foundational goals more effectively than ever before.
What an incredible scope we've covered today. From the bedrock principles of Vitruvius through Roman ingenuity, medieval mastery, early management struggles, right up to the bleeding edge of BIM, digital twins, generative design, and these visions of smart, responsive cities. It really underscores how human ingenuity just keeps building on itself, doesn't it? Adapting, refining, always reaching.
It truly does. And reflecting on this whole journey, the synthesis of past and future,
Yeah.
it really poses a profound question for us moving forward, doesn't it? If that timeless wisdom, say from Vitruvius, taught us the importance of designing holistically firmness, utility, delight, all intertwined, and if our modern tools, like digital twins, now give us this unprecedented ability to see, simulate, and predict almost every aspect of a building or even a city before it's built,
Yeah.
does this mean we are finally truly equipped to design not just buildings, but perhaps entire ecosystems, entire societal systems, with that same level of precision, foresight, and deep holistic understanding of their true long-term impact? Are we ready to wield that power wisely?
Wow. That is a powerful thought to end on, a real challenge for the next 100 deep dives, perhaps. So, as you go about your day, maybe look at the buildings around you, your neighborhood, your city, with fresh eyes. Think about the layers of history embedded there, the human ingenuity, and the future possibilities waiting to unfold. Every structure tells a story, and you, our listener, having joined us for these 100 dives, you're now even better equipped to read and maybe even help write the next chapter.